start with the isotropic and homogeneous assumption that the universe is that way, and in a particular direction that we look at, the universe looks isotropic and homogeneous. So, जहाँ पर भी देखते हैं universe एक जैसा ही दिखता है, it is expanding like a bubble or so. All these things are there in astronomy, and today's session will not be talking about the details of everything, but आपके जो भी questions होंगे, you can certainly throw them at the speaker and me. So for me, you can ask any questions related to particle physics, high energy, that have to do with astronomical data and all. And for Anshuman Bhaiya, you can ask any question related to anything per se, whatever you want to know in astronomy. Okay, please don't ask him about his relationship status and all, hopefully. Okay. Okay, so over to Anshuman Bhaiya now. You can start with your presentation for the first 15 minutes or so, and then later on we can discuss. Yeah.
Yeah. Okay. Maybe I'll just share the entire screen. And now, now the first slide should show up.
Yeah, we can see it.
Okay, perfect. Yeah, so as you mentioned, we would be talking about a lot of things today. So I thought that it's better to kind of frame my perspective of things, like what exactly has shaped my ideas and what has shaped my background so far, and then kind of go into what I do currently and what are the things that I found interesting that could help from the high school level. So yeah, we, like a lot of people here, would be wanting to go on this journey to become an astrophysicist. And as someone who's a final year PhD student now at the Max Planck Institute for Astrophysics, after doing a bachelor's and master's in physics with a minor in astronomy at IISc Mohali, I think I can kind of share my perspective. So yeah, I did my BSMS in physics, and IISc Mohali introduced the astronomy minor for the first time for our batch, and I was one of the first people to get it. So that's where I started from. Because I found that, like, for a career in astronomy, having a solid background in physics was extremely important, and that's what I was able to get from IISc Mohali here. And I applied via KV there. That's not there anymore, and now IISERs only take students via the IISER aptitude test. Like, in fact, from this year onwards, that's the sole criteria that they follow. Earlier, they used to also take students via JEE Advanced, but it was already in going to be phased out, and now it has been. And the coursework was essentially that we had 2 years of all physics, chemistry, mathematics, and biology, even some interdisciplinary courses, which also involved a little bit of, say, programming, a little bit of engineering, and things like that, and also humanities and social sciences. And then we had 3 years of physics with specialized electives, where I could take electives in astronomy as well. And of course, a little bit of humanities courses just to keep things a bit sane. And the final year was a master's thesis project. So one of the key things that IISERs and institutions like IISERs, like NISER, IISc, SEPS, and IISERs have been trying to promote is that in every summer, there would there's a culture of going for research internships. So in the first summer, I really wanted to do something in physics, if not as astrophysics. And I ended up in an experimental condensed matter physics lab in TIFR. And while it wasn't actual research, it was just exploration to a certain extent. It was still quite interesting, and I learned a lot about even very basic fundamental topics, like how exactly does friction evolve, like from, say, sliding to rolling friction, which is pretty cool. Then in the next year, I went into a proper astronomy project. I was visiting a professor at the University of California in Santa Barbara, and there I talked to a postdoc who happened to have certain ideas, and those discussions continued, and we ended up actually building a completely different project out of it. In 2019, I came to Germany via the DAAD WISE Fellowship to the University of Heidelberg, where I was doing computational astrophysics, where we were trying to merge two galaxies with two supermassive black holes in the center and try to see how exactly do the supermassive black holes interact with each other. And then for my master's, I was working. I tried to do something different. Like so far, I was doing computational astrophysics. Like I was simulating astrophysical phenomena. But for my master's, I wanted to do something different. I wanted to actually gather data, like actually look at data that we see. So I looked at stellar X-ray data from the Chandra telescope, and we did a bunch of statistical analysis to try to see if we can find traces of the star interacting with its planet. So it's a way of studying exoplanets, and if we could actually see that interaction play out in the data. So a key thing that I was discussed was that the astrophysics does involve a lot of data analysis, and it involves a lot of theories and everything. And that means that in the end, things are not so simple. Like the time it takes for you to work on something and actually get something out of it, like we got a research paper out of it, which was accepted in 2021. So around 2 years later from when I started. And then the one that I worked on in 2018 in Santa Barbara, that was also in 2021. So two different, separated by a year in terms of when I started it off, but the projects finished roughly in the same year, about 6 months apart. So that kind of gives a frame of reference of the time scales of what it takes to actually do things in astronomy. So there's a lot of fascinating stuff, but actually to get research outputs can sometimes take a few years, but the overall process is worthwhile. Yeah, and because, for example, from my master's, we ended up actually having 2 publications, which was pretty cool. One of them was just about a simple Python package that we developed for analyzing our data. And we both were in, one was in 2023, the other in early 2024, which are almost 3 years after I started, but still the results have been quite fascinating and probably one of the most well-researched papers that I've written so far. So now, as I mentioned earlier, I'm doing my PhD in astronomy at the Max Planck Institute for Astrophysics, and here I'm doing a bit of both things that are important in astronomy. One part is observations, looking at the data out of telescopes, and the second is to build simulations. And then you kind of try to see, okay, if I feed in these input values to the computer, this is the output I get. How does this output compare? Like if I get a photo of a galaxy, how does it compare with a photo of an actual galaxy looked at from a telescope? That kind of gives you an idea of if the input that you're giving, like you know what you're giving in. So you know what is the physics that is going inside your computer. So that gives you an idea of how exactly should you change the physics to get the kind of observations that you're actually seeing. So this gives us a very simple tool to understand the physics that can happen to give the observations we get from telescopes. So we are trying to combine these two things together. So we are trying to say that, okay, if we try all the possible combinations of physical parameters, physics and everything, and build a large set of possible photos of what we can see from the telescope, and then we train like a machine learning algorithm on that, then can we use that as a setup to basically look for something specific in our data? And that's basically what I've been doing in my PhD, and I can talk a bit about it later as well if people are interested. Like, we can just go quickly through it. So the essential idea is something very, like the title seems very long, looking for the transmission signal from the epoch of ionization using machine learning. So a quick primer through that would be that the epoch of ionization is essentially a phase of the early universe. So the universe as we know it, or as we understand so far, it probably started from the Big Bang. And then it expanded, there was inflation, and eventually you had all these particles slowly starting to come together. So you had the protons and electrons start to come together, and they formed the first hydrogen atoms. But then there was just hydrogen atoms everywhere. So that's the phase that we call the dark ages. And then eventually these atoms also started coming together. They formed the first gas clouds. And in these gas clouds, you eventually had the first stars forming. So in these clouds, when the first stars and the first galaxies, black holes, and everything else that we know in the universe started forming, what they did was that they released photons. These photons would again hit the remaining neutral hydrogen in the gas clouds and then again make the protons and electrons separate. Because the photon is giving an energy, so it makes the electron move away from the proton and then they are again ionized. So what we see is that we expect that in the dark ages, everything is in the form of a hydrogen atom. And in present day, we see that most of the universe, the protons and electrons are separate. Like if you call it as a hydrogen atom, you would say that it's an ionized hydrogen atom, even though it's just a proton. And we are interested in this period in the middle where most of this hydrogen atoms got ionized. And we call this the epoch of the ionization. So why are we interested in it? Well, before that, I'll say what exactly I am trying to do is that usually we have the James Webb Space Telescope. It's looking for the earliest galaxies in this period, and it sees something like this. Like, okay, these are the galaxies and everything. But that's not all the information in the picture. Like, these are the bright parts. Cool. That's what we see with James Webb. But what about the rest of this picture where, like, it looks dark, but that's just because it's just gas. It's not emitting photons. But it can still have information. And knowing that information can tell us how the surrounding these galaxies and everything formed in it. And that is why this period is important. This is a period when the first stars, the first galaxies, everything formed. So how fast did it form? What formed first? Like, was it that there were first so-called galaxies, which are just clouds of gases clumped together, swirling around, and then the first stars formed? Or did the first stars start forming earlier, and then they came together to form galaxies? We don't have the answers to such basic questions either. And the rate of formation, like how fast did the first supermassive black hole form? We do not know that. So knowing these things is important, and the way to know that is to look at this period. And one of the ways we use is that we want to look at the neutral atomic hydrogen, and one way is to look at something that we call the 20th centimeter line, and that's what I call the 20th centimeter signal. And this is something that is very cool and creative that astronomers came with to essentially look at the dark patches of the sky, like essentially where you do not expect any photons. We say that yes, there are still some photons there, and I'll explain why. So eventually, when you learn about quantum mechanics, you learn about one of the quantum numbers called the spin quantum number, and both the proton and electron have some spin associated with them. And this spin gives a small magnetic dipole moment to each particle. So each of them has some magnetism to them. And if the spins are aligned, it means that their magnetic fields are also aligned, and they would kind of have a tendency to move upwards, because like in this case, we are saying that, okay, the fields are aligned in such a way that they push each other upwards. But if you kind of have them to be anti-parallel spins, then the magnetic fields can actually cancel out. Then the overall atom would not really have any motion. It will be more less energetic. And that usually is the state that any system in the universe likes to be in. Any system that you have would want to minimize the energy that it has. And thus, you could ideally say that any atom which has the spins aligned would want to cancel it out and then be in a relaxed state. But the problem is that the difference between the energy levels of these two states is very small. Like if you convert this to a wavelength, the wavelength comes to be 21 centimeters, which is where the name comes from, which comes at the radio signal, or a bit higher than that. So what this means is that usually you would not see an atom going from this state to this state by emitting a photon, which is shown by the red squiggly line next in the bottom half. It would usually just hit each other, like one atom hits another atom, it loses some energy, the other atom gains some energy, and that keeps on happening. This is what we see on Earth if you look at, say, a balloon filled with hydrogen gas. But there are still ways. So when we say forbidden, like essentially we say that collisions basically make it de-excite from the higher energy state to the lower energy state. But you could also release a photon, and that can happen when you try to avoid collisions. So how can you avoid collisions? Well, you can have really low densities. Say, for example, just take one atom in a 1 meter cube box, and just that atom is there. Now this atom cannot really collide with anything else. And instead it has, if it wants to lose energy, it will have to release a photon. And secondly, if you have lots of such atoms, like all separated out, very low density clouds everywhere, then you eventually have enough photons, and now you can detect them. So low densities and lots of hydrogen is how you detect continuous of photons. And what we expect from the universe is that in the early universe, there was basically lots of hydrogen spread very thinly across the entire universe. So we should be able to find these, and that's pretty good. Like what we cannot see on Earth can actually be seen if we look from our telescopes pretty far away. And what we want to do with machine learning is that, as I said, that we want to run a range of computational simulations and train our machine learning algorithm on that and try to look for the signal in our data. So we look at, say, simulated data, real data. Like we first do a lot of testing with simulated data so that we build a mock case and see if our machine learning is working fine or not. Then we apply it to the real data. And these results are fairly reasonable. But the problem is that this signal is really faint. What we are trying to look for is a signal from the universe when it was just 1 billion years old. So we are trying to look back almost 12 or 13 billion years ago. And that can be a lot. So this is like, I would not go too much into detail about the plot, but essentially the points show what we believe is the maximum upper limit based on our observations. And the blue lines are what we get from our simulations. Like if we change the simulations to extreme values, then the signal that we expect could look something like the dashed line or the dotted line or the dashed dotted line if we take a very extreme case. We are still far away, but we are improving. As you can see, the most recent points like the dark gray points or the dark red points on the left-hand side, they are slowly closing in. And that's already very good. And in a few years, if we increase our observation time, which is shown by the red line, like this is where we expect it to reach if we observe for longer durations, about 1,000 hours of observations, then we should be able to get a detection. And then we can run simulations to explore what exactly are the physical parameters that we need to feed in to get the kind of results that we see. And there are some problems in that, like all simulations assume the parameters of the lambda CDM model to have a specific value, and then people are not really agreeing on the specific value because different experiments give different values. If we look at, for example, the Hubble parameter, if we look at the local supernovae, we get some value. If we look at the Planck's cosmic microwave background results, we get a different value. So we want to kind of look at all the possible cases and get an answer. So we are running these simulations. We are looking at it with different parameters. And then we are also looking at, if we change the parameters, what kind of galaxies do we form? Do we see those galaxies in the James Webb Space Telescope observations? So we run something like this. We run these on supercomputers. We essentially have, like this is just dark matter, and we let it evolve over time. We see that it starts clumping in, like basically wherever it's brighter, there is more number of particles. And I'll just increase it. So slowly we form the cosmic web. And at the center of these webs, where it starts getting brighter and brighter, is where the galaxy clusters form. And we are zooming in now. And this is essentially, like if you look at this part here, the central part is where the central galaxy will form, and the brighter other parts are where other smaller galaxies would form. And this is what our simulations are showing to us. Now what we do is we put in, like we add in other physics to it. Like here, this was just dark matter. We then add ordinary matter to this. We add how does gases flow around with basically adding in fluid mechanics, radiations and everything. And then we can get our results which we can compare. Sorry. Uh, yeah. One second, something is going wrong. Yeah. Yeah. Now, like I saw a lot of questions, and we can probably go through these, and maybe I would. We can just actually just start with questions, and I can just after a couple of minutes, maybe I can just say that in terms of courses, I would say that there are these courses in physics at many places for an undergrad. And if you end up taking say a BTech degree, then there's also the possibility to still switch. But typically you would do a master's in physics with, say, a research-based master's thesis component before you can delve into astrophysics. And of course, the next step would be a PhD, because if you want to go into research in astronomy, you would need the first essentially entry-level job in research, which is a PhD. And there were a lot of questions, like I saw the questions that you all submitted. There were a lot of questions about books and everything, and we can kind of discuss them later, but I had a list of them prepared that you can look at. So, like some of the cool things about each of these books was that Fundamental Astronomy by Kartunen is actually free, like the PDF is available online. So many universities also host it because it's a very fundamental book, as the name suggests. If you want something by Indian authors, I can recommend this book, which should be available on Amazon. And then if you want something which is like a popular science book, but it's kind of different from the most common ones that you find in, say, places like Stephen, like I'm not mentioning books by Stephen Hawking or someone else, because you would have probably seen those. So these are some of the recommendations, and even on YouTube, you can find a lot of interesting channels that cater to astronomy. Like there's Dr. Becky, who essentially talks about a life of, as an astrophysicist. Cool Worlds is basically run by a professor at Columbia University who talks about his own research and his group's research on topics of astrobiology and exoplanet studies. PBS Spacetime is a general astrophysics channel, and Kurzgesagt is basically a channel for general science, but it also covers many interesting topics related to astrophysics. And similarly, Science Time is also a general science channel, but definitely something that you can take a look at. And lastly, I would just talk about careers in astronomy, because that's also a popular thing. So as I said, you start off with a PhD, but because a PhD in astronomy involves so many things, it involves physics, it involves statistics, it involves data science, programming, and depending on how much you do, maybe even computer science background, even hardware knowledge, a lot of people are able to and prefer to transition to other roles because they find something else interesting. So going into jobs in tech, jobs in finance is very common. So depending on where you look at, about 25 to 75% can actually leave for other jobs, or even industrial research. Like for example, they like to do research, but they like to do things with data. They are not really concerned about what they do with, like where does the data come from. So those people can go for other jobs, while the remaining go for the next step in astronomy research or any field's research, and that's the job of a postdoctoral researcher. Here, you are still tied to a professor, but you also supervise students, so you get a flavor for how does it feel like to lead a project, to help a student work and understand a project and develop it into something that can lead to actual real contribution to research. So once you have that kind of experience, you apply for professorship, and you are in the tenure track, which means that based on your performance, you would be given a permanent job, and at this moment you would be supervising your own students, maybe even taking courses. But yeah, even here, some people leave, like after getting some postdoctoral experience, they're like, okay, I like supervising people, but maybe I do not really care too much about if I do it in astronomy or if I do it somewhere else. And then, of course, like from tenure track, you move to the permanent jobs. And leaving at this point is low, but again, you never know. People have interests change all the time. These roles are, something, okay, sorry. Yeah, something cool because of the amount of data and data analysis that is involved, and even hardware development that is involved in astronomy. Some people also end up setting up their own companies. For example, the first interferometers for radio astronomy were used for essentially ensuring that your signals mesh together correctly and then produce a stronger signal. This was first applied, like the person who did this in astronomy then moved to medical research and applied this for things like MRI scanning and other things like that. And then they realized that this could actually be used for something else. And that something else was how the technology of Wi-Fi was built. Because if you have a Wi-Fi router somewhere, how do you ensure that the signal goes around to other rooms? Just a second, I'm not able to see the screen. Just a second. Yeah, cool. Yeah, we can continue from here. And usually these roles are in universities, and but like it's not limited to universities. You can also have research institutes like my institute, Max Planck Institute for Astrophysics, is a research institute and not a university. You can also have observatories, planetariums, and museums, where the name of the roles change, but the basic idea remains the same. And there were some questions which were confusing what an astronomer does or does not do. And that is like, for example, space research organizations which facilitate space research, and their involvement is basically on building space technology, like ISRO or NASA. They are not usually where astronomers are employed. Sure, there are some, they have their own research institutes, like NASA particularly has a lot of research institutes where they do focus on astronomy research, but the primary work of NASA is in the end space technology, and that's not what astronomers do. Secondly, we do not do space missions, at least not yet. Astronomers are not the ones who would go up and be an astronaut, because we are perfectly happy to remain on Earth, look at things with our telescopes and try to understand these things. Now, if you have more questions, we can honestly just go ahead with that, and I can just stop sharing and kind of do it in a more interactive way.
I think this was a wonderful introduction to every question that one could ask when it comes to astronomy. But I think for high school students, these people would not really, I don't think they fully understood your research part. They might have.
Yeah, that's perfectly fine.
Yeah. I think for them, we could dumb down things to a more basic level. Maybe what we can start with is describing the early universe. Okay, so the question of Big Bang. This is a very typical question that everybody keeps asking. What really happened there? Why do you start the universe start? So one very interesting question that somebody asked was whether the universe is inside a black hole and not really started from a Big Bang. Because we can't go inside a black hole, so we don't know whether or not we are inside a black hole ourselves. So maybe you could have something to say about that.
Yes, so we can start from there. So basically the idea of the Big Bang is kind of an extrapolation. So what we do know essentially is that if we move backwards in time, like the idea is that if you look with a telescope, if you are trying to look for a photon from the early universe, it would have taken longer to reach till you. So it would essentially, if you are able to see the photon, it was released at a point of time when the universe was much younger. So that's kind of a way to look at the early universe. And when we look at the early universe like that, we see that things seem to be closer together. Things seem to be more closely packed. And if we keep looking further and further until we reach the cosmic microwave background, which is the earliest observation that we have, we see that everything was much closer together. And while it was still somewhat homogeneous, we did not did not expect it to deviate from anything that we see now, and that is that everything that we see today is still clumped together in similar ways, just expanded. So we could kind of get this of an idea that, okay, first universe was more clumpy, now it's less clumpy, and if everything kept going closer and closer together, at some point it would have been a point. And now this point is essentially like if we scale it back down to a point, then that is essentially what we call a singularity. And the singularity would be like a black hole, sure. But we, as far as we know, black holes do not really explode. So or do not really pop out to give a universe. So far, we do not know that. So then something did happen. The problem is we don't really know beyond the cosmic microwave background. That is about 300,000, like based on calculations, it should be an observation which was about 300,000 years after the Big Bang. What happened in this period is something we really don't know. This is just based on an extrapolation that, okay, if things were closer and closer together, it would be a point. But what do we do with that? So we are trying to find ways to get an idea of what was there before the CMB, but the ideas are limited. And if was it like a black hole? Sure. But why did it behave differently? Why did it explode to give the universe? We do not know yet. So we'll have to see.
Yeah. So something has to do with this idea of dark energy and dark matter also, I believe. That I think the amount of dark energy is much more as compared to that of matter. So I believe
that kind of like was necessary. Like we see some features in this cosmic microwave background which suggest that we need dark matter. Otherwise, just matter's clumpiness is not enough to explain the cosmic microwave background's like temperature fluctuations. So that kind of gives us an idea of the dark matter presence, and dark energy was needed essentially to see that, okay, when we look at our observations, we see that even if we say the universe is expanding, there is gravity which is trying to pull things together. But we actually see that the expansion is accelerating. That should not happen. At least the expansion of the universe should have been balanced out based on our calculations. So we needed something extra, like the universe needed something extra, and for now we just call it dark energy. We do not know what exactly it is, why does it exist, where did it come from, and what role does it play overall. But we are trying to learn more about it. But at the moment, we call it dark energy.
Yeah. There's also this question about, when the universe was formed, we had equal amounts of matter and antimatter. But now it's matter that prevails more. So there is a possibility, slightly, it's just a speculation, that somewhere else in the universe, in some other corner, there are galaxies made of entirely antimatter. And since the universe is expanding, they would not, as of now, interact with matter, because matter and antimatter, they annihilate together. So it just stays as it is in some corner of the universe, which we are not able to observe. Perhaps it's farther than what our telescopes can see, but it's still in speculation. Yeah. So that's one idea.
Yeah, that's something that we do not really understand that fully, and the problem here essentially is that, okay, sure, matter and antimatter should have been equal, but currently it is not. Is it kind of like a situation where we have a local region, like essentially the entire observable universe is what we call as local, where matter is dominating? Is that the case? And like if we just because the universe is expanding so fast that light from certain regions is not able to reach us anymore, maybe that region has something of antimatter. We do not know that yet. But we can, things that we can look at is, there are many experiments which are trying to look at these things in a way that is slightly more indirect, more difficult, but still that could give us a better picture. Like, for example, looking at neutrinos, because neutrinos are able to pass through a lot of things without interacting much. So maybe, just maybe, we are hoping that if their behavior with matter and antimatter has some difference, or if they form their antiparticles in a certain way, then maybe we could glean some information out of it. But at the moment, again, there's a lot of... The key and most interesting point of astronomy is that there is more that we do not know than what we know. There's just a lot of unanswered questions.
Yeah, I think that has to do with most of science anyway. So anywhere you go, today we were having an interesting talk on biology, evolution, and ecology. So the professor who came was discussing about bees and wasps and the behavior. So how a queen comes up in a particular colony. He had hundreds of questions. The guy wouldn't stop for 2 hours. I sat down there accidentally and had to listen to him talk about ecology for a very long time, and the questions would not end. So the point of science is there are more questions to answer when you have time to think about those questions in the first place. And you mentioned about neutrinos. So the interesting thing about particles here is that, so I work in high energy. For everybody who's here, they can understand. In high energy physics, what you basically do, so Anshuman Bhaiya researches everything that is already there, okay, and he tries to figure out the answers of the universe in a pretty early stage. For high energy physicists, what we people do is we try to recreate those in particle colliders. So at LHC, at CERN, basically at Large Hadron Collider, or even at RHIC at BNL, we collide heavy ions or we collide particles, try to recreate those initial conditions of the Big Bang, and then try to understand what kind of evolution that gives us, and then we try to answer all those questions that are in that black period that you said. So after around 300, I think you said 300,000 years, right? So that is
300,000 years was when we got CMB.
Yeah. So we try to recreate everything before that, and then we try to see how QGP formed, quark-gluon plasma, and everything. So there's a nice, I would say, intersection between astronomy and high energy physics. So everything we do on Earth has to do with high energy, and everything that we do in space has to do with astronomy. So people who are interested in both of them can certainly find an intersection between the two and see where that takes them. And So the other very interesting question that somebody asked has to do with, are those images that recently JWST released a lot of interesting images, are all those images colored images? You see, telescope is basically just a large mirror sort of object. So does it capture everything in color? Because when we look at it in a mirror, mirrors are basically just giving us colored images. Are telescopes also giving us colored images? You can answer that.
Yeah. So the JWST is a telescope that is built to look for light in the infrared regime. So the infrared is essentially less energetic than the visible spectrum. So that would put it somewhere like everything that if you actually look at the real color and you would not actually see anything, because only the reddest parts of it would be visible. Beyond that, our eyes cannot see what the telescope is seeing. What they do is that they push, one way to look at it is to kind of push the entire spectrum into the visible region. Then the images that you get would look essentially something from, say, very, very dark red to yellowish. Now, you can also add more information to it. You can say, this is what actually goes in and looks like real images, but not exactly. And that is that if you want to, like a scientist wants to look at, say, how much of the image that we are seeing, how much of it is like really cold gas, because that's where you would have atoms and molecules forming, and he would assign a color, like, okay, let this be whatever is the very cold gas, I'll say blue is a cool color, I'll add a blue color to it. And then they say, now I want to look at kind of slightly warmer gas, and then they put that color as green. And because there many molecules don't form, but atoms can still exist. And then they leave the red for the hot gas, which is where everything is ionized. So that kind of like composite imaging gives you the kind of images that are released to the public. But yes, if you actually look at it, it would be just red splotches. That's what the actual image is being seen by the telescope.
Yeah, so it is mostly false color. For all those telescopes that look beyond, let's say, not within the very small spectrum of visible light. So for everybody, class 11, 12, those people know what electromagnetic spectrum is. But if people are from class 10th here, so you basically look in what we can see is in a very small spectrum of the large electromagnetic radiation. If there is any telescope that looks beyond that, it has the sensors that can probe the universe or any particle coming in or any photons coming in. In the spectrum that is not the visible spectrum, you have to employ false coloring. Or as he said, there is a certain scheme or a template that astronomers use to give it a sort of color that our eyes can interpret. And certainly there can be different color schemes for different observations. So you want to look at certain parts of the spectrum, you look at that. So that is basically the idea about that. There is a question here. It's a very interesting question. It says, if a black hole's gravity is so high that even light can't escape it, then how did we detect the first black hole? Okay. So
yeah, that is a perfectly valid question, but it is answered by, like, it was answered by Newton himself. Like, black hole's gravity is high, but if you're that's when you're right next to it. If you go further away enough, you can reach a point where light can just escape, and that's what we call the event horizon. Yeah. So the light that people say that for example, essentially the images of the black holes that were released, those were by people who looked at the gas and the really hot gas which was being slowly churned into the black hole, and because the gas is being heated up when it's falling in, it was releasing photons, and this is the distance at which the photons can just escape. So you are looking at the picture that was generated by all the telescopes together was just outside the event horizon of the supermassive black hole. So it's not a picture of the black hole; it's a picture of everything around the black hole. So that it is definitely a valid question, but so that is kind of a small clarification that it's not just the black hole that we are looking at; it's much more than that.
Yeah, so it's not the singularity that you're looking at; it's around the singularity. So I think Veritasium was a very good explanation about how we got that accretion disk image of the black hole. If anybody yeah, that's a very, very wonderful. I enjoy that video so much. There's a question, it's a long question. Let's see if it makes sense. It says, so if I throw a subatomic particle in the universe which has mass and obeys the laws of quantum mechanics, every particle does that, okay? And the speed of the particle is very high, nearly the speed of light. So the expectation value of momentum increases as the mass of the subatomic particle increases and it starts bending the space-time curve. So is there any relationship between the warping of space-time and the expectation value of momentum? Okay. I don't sure. Yeah, okay, maybe you can answer this. Do you want to?
I mean, you don't have to look at the expectation value of momentum. It's just the fact that if it is moving at the speed of light, and then it has its speed itself would not really change anything much. It's what would matter is its mass, and sure, if it builds up enough, if the mass is small, but you inject enough energy, the overall thing, which is what leads to that kind of speeds, then it would, the overall mass plus energy can be significant enough to cause bending. But this is essentially just a feature of mass and energy. And sure, you can frame it in terms of momentum, but momentum is just a mathematical quantity we use to explain the relation between mass and energy. So it's not really something that is physical per se. It's just something that we use to do our calculations.
Yeah. So what you can deal with is the form momentum that deals with the energy mass as a whole, right? And for the one who asked this question, you don't really have to talk about expectation values here, but because in quantum mechanics, expectation values are what you get when you do an experiment or when you do a measurement, right? So that was slightly a bit of a detail. Maybe you missed that, but that is completely fine. Then I believe there's another question. It says, how exactly is the universe expanding if we say that the total energy of the universe is constant?
I mean, if there's no harm in it expanding if the energy is constant, but the thing is, it is a bit of a tricky thing. Like we know that we do not really say that the energy of the universe is constant. We say that if we take a system anywhere, if we define a system in a certain way, then it should have a constant energy. And we think that, okay, these kind of systems where everything is homogeneous, everything is isotropic, blah, blah, blah. If those kind of systems are built, then if it's similar to the universe, then maybe the universe has a constant energy. But that's not something we actually know. And the fact that we had to inject dark energy into the equations for explaining the universe shows that that's not really something that holds true anymore. Like the idea of dark energy is to say that yes, there is something extra which is added on that can change things up. So we do not, what essentially it means that if we do not fully understand what the universe is made up of, we cannot really make claims that it's constant or not. So and even if it was, you can have expansion, just the energy is driving things apart, like the same constant energy can have localized differences. Like
Exactly.
Even if the overall system has constant energy, you can have regions where you have more energy, regions where you have less energy, and that would change things inside. And then that itself would give you expansion. And that was what we expected. But then we found that no, expansion is not just this much, there's acceleration and expansion. And that's where dark energy came to the picture.
Yeah, that's what Hubble discovered when he was working on this. Yeah, when he was doing his research. And to talk about this energy, you can also understand this from the entropy point of view. So if you study statistical mechanics, which I'm talking about the students here, when you do, you will understand that overall the entropy of the system, whenever you treat a system, that has to increase then to a maximum value per se. But locally, the entropy of a system can go through can spontaneously decrease also. So it's the larger picture of the overall system that you have to look at, and not particularly a small piece of section. So whenever we are probing the universe and looking at the expansion, you don't only look at one particular point in space. You look at a very large range of points in space. You look at very large spectrum or very large value of data. That is what you look at, and you do that for any experiment. Okay, so science, if you want to do, you just don't look at one particular set of data. It might be that one particular set of data was completely flawed and completely screwed your experiment. So you have to look at a large value of data, and then you average it out and what do different sorts of analysis and model it, and then you see what it turns out to be. Okay. And I believe now there are a lot of questions about the expansion of the universe. We can completely skip those. If black holes are formed due to collapse of stars, then how supermassive black holes were formed? This question, Aditya Das, you can look this up. It's you have to look at the Chandrasekhar's limit, okay?
Yeah, but the thing is, for supermassive black holes, there are actually multiple explanations, and we do not know which explanation is the most dominating form. So the supermassive black holes are actually, we are still not sure how they are formed. We have multiple explanations for it. But for example, you could just form stellar mass black holes, like those formed from stars, and then keep merging them together until you form a supermassive black hole. That's the easy solution. But there also are more complicated solutions out there, and we do not know what exactly is the best way to make the central supermassive black holes. We have the Chandrasekhar limit for explaining black holes which are formed from stars, larger stars, etc. But the central black holes, we don't really know for sure yet. So that's actually a cool question still.
Oh, here's a very interesting one. So someone is asking that if you look at a very old television, right, they have antennas and all. So the static that they get, do they have parts of the cosmic microwave background radiation?
Yeah, I mean, definitely. So like basically the cosmic microwave background radiation is, as it says, is a background radiation. So it can be everywhere. And what this means is that wherever you have, like, if you just point at antenna and it can essentially receive that kind of signal, it will have that come in. But then we have a lot of other signals, like what the static that we get is essentially a lot of the noise from the radiation that we are sending for the televisions, like what the radio signals that the television receives. But there is also a little bit of the cosmic microwave background in that, because it's just everywhere.
And then by radiation, he doesn't mean any radiation, but it's just photons, okay? So there are multiple kinds of radiation. We have alpha radiation, beta radiation. So photons are what we have in cosmic microwave background radiation. Okay, so I think this question applies to everybody, and he should certainly answer this. And he did in his presentation also. What about coding? How much of it do you need? Or do you start hardcore coding when you're in high school? How much of coding do you exactly need? So these days, if you are doing physics, theoretical, be it or experimental, without a computer, you are doomed pretty much. So, Anshuman Bhaiya, please just let them know the.
Yeah, so in 11th and 12th, I did take computer science, so I learned C++ there, but it's not something that is universally true. There are a lot of people who enter university without having knowledge of programming, even like PhD, people go into PhD with limited knowledge of programming. But in today's world, in field, especially in fields like astronomy, astrophysics, or even high energy physics, where you're dealing with these large experiments, large amounts of data, how do you analyze the data? You cannot sit down and look at each picture, each data point separately and manually do these things. You need to use computers. So the first and most important part is data analysis and data representation. How do you take in the data you're getting from your telescope or collider or anything, and then analyzing it to get what is it's actually trying to tell you, like what is the information out of the data. Next, you want to show that to other people. They should be able to understand what you got. So then it's data representation. So you make plots, you make graphs out of it, and you show it to them. This part is where people nowadays use Python or even Julia to a certain extent for programming. And then in physics especially, we also have this problem that we cannot always run an experiment. For example, in astronomy, this is especially important, that we cannot run an experiment of, for example, if you want to take two galaxies and merge them together. If you just look at observations, you would have to observe two galaxies for millions of years to be able to see this. And this applies to like pretty much all aspects of astronomy. Like, for example, if you want to look at a planet, how did it form? Planets take billions of years to form. So you can't really just look for billions of years. So we try to do these things, like if you want to look at the theoretical explanation behind how planets form, how galaxies form, these kind of things, you would want to do simulations, which is where you feed in the physics to the computer and you try to simulate the experiment. So for these things, even Python is not always the most helpful, because Python essentially is built on top of other programming languages. Like it borrows from other languages and then does it, and because of that, it has to ask the other code, get it, and then give it to you. So it takes time. So then knowledge of other programming languages like C, C++ can be helpful. But at the same time, it doesn't mean that you need to learn all the languages altogether. You can essentially start with one, slowly grasp how does the basic programming work, and you don't need to be like, okay, I want to learn programming for astronomy. That's not how it works. Just try to pick up something basic in programming, start building experience, like basic general problems from online courses, YouTube, or anything, and even books. You can start with that, and then gradually build from there to see what is needed for your interests, and you can evolve from there. So you can even start with Python, and then once you have an idea of how programming works, how the syntax of Python works, then you can also look at, say, C, C++, or anything else, which is perfectly fine. Like you don't need to know all the programming languages from the start.
Yeah, so that answers a very important question, and it is for every person who's interested in physics. I'm very serious. Do not take it lightly. If you want to go into physics, get some idea about coding. It's an important skill to have. There's no point in learning it if you already are aware of facts that you have to do it. So you sit down maybe in your masters to start learning what you have been told to start learning from your high school or something. Okay, so this has been a wonderful session. I had really a lot of insights in it. And I'm in my third year, okay, so I believe class 10th, 11th, 12th students had a lot of insight as well. And I'm sure you have a bunch of questions that need to be answered, but time is something we have to respect. And I believe you can contact Anshuman Bhaiya. I think he has mentioned his email somewhere in it. So please
maybe I can, if you want, I can briefly show that.
No, I think they can go back in the video if they're
you're on YouTube as well, so
they might spam you with a lot of emails, so let's not do that.
Yeah, maybe you can just go, like if you look me up online, like Anshuman Astrophysics or something, my website should come up. You can contact me from there.
Yeah,
that's
Anyway,
Yeah,
we
worries
will
about
be
that.
having a physics series on SciAstra anyhow, so people can ask their questions whenever they want. And we would now like to thank the speaker. Thank you, Anshuman. It always is a pleasure to interact with you. Wonderful. I truly enjoy it.
Thank you so
Thank
much,
you. That
Bhaiya.
was like it was really really nice.